Hi everyone, I'm Xindong, a Master in Biometric Technologies Lab, U Calgary, Canada. Today I'm going to present my paper, Adversarial and Adaptive Time Mapping Operator for High Dynamic Range Images. This work is finished together with Ken, a PhD in our lab, Dr. Svetlana Yanushkevich, my supervisor, and Dr. Mike Smith, my co-supervisor. This work is in the computer vision field, involving image translation for high dynamic range images. In the next pages, I will first formulate the objective of this paper, then I will detail our proposed method, conditional generative adversarial network for image translation and how we process our dataset. Then I will show the results and finally go to our conclusions. The objective of this paper is to build a time mapping operator to adaptively convert high dynamic range images into low dynamic range images. Here I give an HDR image and an LDR image to help you understand. I should mention that HDR images can't be displayed by most devices, so here I apply linear normalization to this HDR image. So what's the difference between HDR images and LDR images? Generally speaking, LDR images use an 8-bit integer to represent per pixel per channel of an image, and the pixel value is between 0 and 255. So the dynamic range of such images is between 0 and 255. As for HDR images, they use a 32 or 64-bit number to represent per pixel per channel, and the dynamic range of such images is much higher. Though HDR images are more accurately matched with real scenes, they can't be displayed by most common devices, so we must convert them into LDR images before displaying them. And it comes to time mapping. Time mapping is one of the common methods to convert HDR images into LDR images. In the past 20 years, several time mapping operators, TOMs, have been designed and have shown success in some specific applications. Another question is how to evaluate a TOM. There are two ways, subjective evaluation and objective metric. In this paper, we will use an objective metric, time-mapped image quality index TMQI, to evaluate our proposed TOM. TMQI represents a form of indexing that considers the naturalness and structural similarity of both HDR and time-mapped LDR images, and it has shown good correlations with subjective evaluation. Also, TOMs have several weak points, such that they don't generalize well with regard to image contents and require parameter tuning. So we propose a TOM that can adaptively time map all HDR images with different contents. With the recent success in deep learning methods and easy availability of HDR images, it is possible to build a deep neural network that can learn the complex mapping between HDR images and time-mapped LDR images. In this paper, we will use conditional generative adversarial networks, CGAN, to solve this problem. In this slide, I will introduce GAN first. GAN consists of a generator and a discriminator. Discriminator tries to distinguish the real samples from the collected data and the fake samples generated by the generator. Generator tries to generate fake samples that are real enough to fool discriminator. By training them together, they can reach an equilibrium so that we can make use of the generator to generate data. CGAN is a GAN where generator is given some conditions. CGAN works well in image-to-image translation tasks, like day image to night image, and given each to generate the whole object. In this paper, we use CGAN to build our adversarial and adaptive time mapping operator. We call it adTOM. This is the training pipeline of our CGAN-based adTOM. Given an HDR image, generator is to generate its time-mapped LDR image. The input of discriminator is an HDR image and an LDR image, and the discriminator is to distinguish whether the LDR image matches this HDR image. In our work, we deploy different training and testing schemes to explore the possibility of training adTOM with low-resolution images and evaluate its effectiveness with low-resolution and high-resolution images. Here is the architecture of our generator. It consists of one input layer, 7 encoding layer, one bottleneck layer, 7 decoding layer, and 1 output layer. Each encoding layer will downsample the previous layer into 1/4, and each decoding layer will upsample the previous layer by 4 times. For each encoding layer and decoding layer pair, we add a direct skip from the encoding layer to the decoding layer and concatenate them. This is the architecture of our discriminator. We use a 70 × 70 patch gain as our discriminator. Each value in the output matrix maps to a 70 × 70 receptive field in the input layer, identifying this patch as real or fake. Here is our objective function. G star is the optimal generator we want to find. Objective function consists of 3 parts: C-gain loss, feature matching loss, and perceptual loss. Alpha and beta are coefficients to control the weights of feature matching loss and perceptual loss, respectively. C-gain loss will direct our generator to generate LDR images that look real. For feature matching loss, we extract features from multiple layers of discriminator and try to match these intermediate representations of a real and generated LDR image. For perceptual loss, we constitute the intermediate features from each single layer of the pre-trained 19-layer VGG network. With feature matching loss and perceptual loss, we are able to make the high-level features of real LDR images and generated LDR images similar. As I said, we use 256 resolution images to train our model. We deploy 3 training schemes. In training scheme A, we resize the original HDR images into 256 resolution to train our adTMO. In training scheme B, we resize the original HDR images into 1024 resolution and crop 256 resolution regions to train adTMO. For training scheme C, we combine training databases from A and B to train adTMO. We deploy 4 different testing schemes to evaluate the effectiveness of adTMO. For training scheme W, we resize HDR images into 256 resolution and use the generator to generate its LDR image. The red box shows the process of testing scheme W. For testing scheme X, we resize HDR images into 1024 × 2048 resolution and use generator to generate its LDR image. The blue box shows the process of testing scheme X. For testing scheme Y, we crop 1024 × 2048 HDR images into 32 pieces, each for 256 resolution, and use generator to generate 32 LDR images individually. The brown box shows the process of testing scheme Y. For testing scheme Z, we concatenate the 32 LDR images in testing scheme Y into a 1024 × 2048 LDR image. The pink box shows the process of testing scheme Z. This page shows our experiment setup. First is about the databases. We have altogether 759 images for training and 105 images for testing. And all HDR images are unlabeled. That's to say we don't have the ground truth LDR images. So we use other terms to generate the target LDR image. For each HDR image, we apply 30 terms to generate 30 LDR images and select the one with the highest term as the target, discard the other 29 images. We also apply normalization to the input images so that the input pixel value is between 0 and 1. And last, we extract luminance channel from the RGB channels to train our adTMO. And we apply color reproduction of the output to get the RGB channels. With all the above setup, we can use a trained adTMO to convert an HDR image into an LDR image. This table shows the generated LDR image of one HDR scene in different training and testing schemes. LDR images in testing scheme W have higher TMQI, while many details are lost in resizing operation. LDR images in testing scheme XZ in training scheme A have lower TMQI with shadows around the trees because we only train adTMO with resized 256 images, as such many details from the original images are lost. After we add cropped images into the training databases, adTMO is able to learn how to keep the finer details of the original images. Therefore, the LDR images of testing scheme X in training scheme BC look more natural and have higher TMQI. The LDI images of testing scheme Z should concatenate edges because cropping a complete image into pieces and generating their time-mapped LDI images individually break the initial connections between these pieces. Because of the above analysis, we decided to use training scheme C to train adTMO, use testing scheme W to generate low-resolution LDI images, and use testing scheme X to generate high-resolution LDI images. This table shows the average TMQI of LDI images after applying TMS to the 105 HDR images in the testing databases. And here I show the 3 worst and 3 best terms for comparison. Our adTMO outperforms all other terms when generating high-resolution images. In this page, I show an example of outdoor scene compared with 3 best other terms. Our adTMO has the highest TMQI. In this page, I show an example of indoor scene compared with 3 best other terms. Our adTMO has the highest TMQI and also doesn't suffer the contrast problem. Finally, we go to the conclusions. In this page, we propose a CGAN-based adversarial and adaptive time mapping operator, which can adaptively time mapping HDR images with different contents, and we deploy different training and testing schemes, use low-resolution images to train adTMO, use low-resolution and high-resolution images to evaluate its effectiveness. TMQI of our adTMO can reach 0.9 plus and minus 0.06, higher than all other terms. That's all I want to share today. Thanks.